Hello everyone, welcome to our channel Code with Sunny, and today we will be discussing the medium problem related to binary search trees. You can see the problem name is all elements into binary search trees. Its index will be 1305 and it is the daily challenge problem of LeetCode January 26. Okay, so so basically I'm going to deal with the two basic approaches to solve this problem. Okay, I will discuss in detail. So one of the concepts that you need to understand, or like that should be a minimum requirement to solve this problem, is the in-order traversal of a given binary search tree, or you can also say binary tree. No, it doesn't matter, but what you need to focus it about the in-order traversal of the binary search tree. So if you are unaware about that, then you can go to this one, in-order traversals, and you need to read it about at least one time so that you can going to be aware about what does the in-order traversal of a tree means, because I'm going to use that frequently in this video, trying to explain everything related to that. Okay, so you are going to search for in-order traversal of the binary search tree using like iterative approach and the recursive approach. I will tell both of the approaches to solve this problem. Like we will be using the iterative approach to solve this problem, like iterative approach to find the in-order traversal of the tree, or as well as also I am going to do the recursive approach to find the in-order traversal of the tree, and then we will coordinate the any one of the method to solve this problem efficiently. Okay, so given two binary search trees, root 1 and the root 2, that is there will be two binary search trees and we have been given the root of the respective trees. Return a list containing all the integers from both the trees sorted in ascending order. Okay, so basically the problem asks us to find out all those integers from both the trees, sort them in a non-decreasing order, ascending order, and then we are going to return the sorted list. Okay, so let's understand what does this problem is trying to convey, and then we'll together build up the best solution. Okay, so let me just draw a tree from this example, like 2, then where he will have 1, and here we go 4. Okay, so let me write down clearly 4. Okay, and again is 103, 103. Okay, so let me talk about the brute force approach, or you can say the implementation, brute force slash implementation. Okay, brute force slash implementation. So that approach would be like find all the nodes in one of the binary search tree and another all the nodes in the another, for the case of another binary search tree. So in that case you will have two vectors or two arrays. Let's call the a1 and a2. So a1 will denote the all the elements present in this binary search tree, and a2 will denote all the elements present in this binary search tree. So a1 will contain these elements. Let me say you are going to do a simple traversal in this binary search tree, so it doesn't matter whether the elements are in sorted form or not. You have this one, a2 as let's say 130, like I am doing a simple traversal and storing all the nodes in an array. Now the question asks us to find out the sorted list containing all the elements from this one and this one. Okay, so what you are going to do is like make another array A and push back all the elements from both the two arrays, 2 1 4 1 3 0. Now we need to return a sorted list, right? Let me write down sorted list. So we are going to sort this array. Let me write down sort array A. Now if you are going to sort this array A, then you are going to get the elements like this: 0 1 1 3, sorry, it should be like 2 3 followed by 4. Like I think, yeah, I'm going in correct way. Yeah, so this will be your answer. So what you if you talk about the complexity of this entire approach, like brute force approach, that is you're going to do whatever has been asked. So you will have the time complexity as you can see. If you there are n nodes in this one and there are m nodes in this one, so traversal takes time of O of n plus m. Okay, and if you have this n plus m, like the entire nodes, and then again you are going to sort this array A. So how much time it is going to take? So sorting an array takes n log n time, at n logarithmic of n, where the capital N is the total number of nodes, which is n plus m. So your complexity will be n plus m plus n log n. Okay, so this will be your complexity, time complexity, and the space complexity would be again the O of n plus m. Okay, so but this approach is not good one, is not the best one. We are going to talk about another best approaches using in-order traversal of the tree. Like if you focus upon here, like the elements are not in the sorted form, right? So what if we have the elements in the sorted form? So if we have the elements in the sorted form, then that will help in merging these two arrays efficiently. Okay, so let's talk about how we are going to get that. Suppose let's say elements we have is like a1, as let's say we are going to have the elements in the sorted form. It should be like 1 2 4. So this is actually the a1 array, and a2 array would be like elements in the sorted form. It should be like 0 1 3. Note that a1 corresponds to the element from the binary search tree 1, and a2 corresponds to the element from the binary search tree 2. Now suppose if we have the elements in the sorted form, like over here, sorted form, and again over here is also the sorted form. Okay, so and we need to find an array A containing exactly 6 elements, okay, and which are going to be in the sorted form of containing all those elements from the array a1 and a2. So what we are going to do is, like, since this both the arrays are in the sorted form, we will compare the very first element of both the arrays, like this one, 1 and 0. Okay, so if we compare, can you just guess it out, what is the smaller of these two elements? So you can say, yeah, this is the smallest one, like 0 is the smallest one. So you will have two pointers, let's say I is over here and j is over here. So you will compare array of I, let me write down, array of I and array of j. So which one is smaller? You can see array of j is less than array of I. So you will pick up the jth element from the array from a2. Okay, so yeah, you need to do this efficiently, like I think a1 of I less than a2 of j. Okay, so you will compare that the very smallest element which is not taken yet. So you can see 0 is less than 1, so your array A will contain 0, and you will move the j pointer to the next step, j plus 1. Okay, so in the next step you can see j is not over this one, j is over this one. Okay, then again you are going to compare this element and this element. So you can see both the elements are same. You can take any of the elements. Let's say I have taken this element j again. So it will be 1, and j will be incremented by 1 again. So j will move toward this position. Okay, and I is still over here. Now if we compare 1 and 3, you can see 1 is the smallest among 1 and 3. So you will pick up the 1 again, and you will move your I pointer to this position. So this is 1 again. Then again you are going to compare 2 and 3. So 2 is smaller, so you will pick up this 2 and move I pointer to the next position. So you will write down 2 over here. Now you compare 3 and 4, you are going to get 3, then again 4, similarly like that. Now this is the sorted form containing the elements from both the arrays. Sorted form of elements of A1 and A2. And what is the time complexity to the merging operation? So merging takes time of, you can see every element is being iterated exactly one time. So it will take a O of n plus m time, where n is the size of array A1 and m is the size of the array A2. Okay, so this gives us the idea that if we get the elements of first binary search tree in the sorted form, and the second binary search tree also in the sorted form, like all the elements, then we can merge those two arrays in O of n plus m time. Okay, this will take a O of n plus m time to sort A1 and A2, and to get the elements in the sorted form of any of the binary search tree will give us the time complexity of O of n, if n is the number of nodes for the first binary search tree, and O of m is the number of nodes for the second binary search tree, and the method that I am going to use is the in-order traversal of the binary search tree. Okay, so let me write down in-order traversal. Okay, so we can use the recursive or iterative way, it doesn't matter. It will take O of n time to find out the elements in the sorted form, and you can store it in the array and merge the two arrays in O of n plus m time. Okay, so I have already recommended you to read about the article of in-order traversal using recursive and iterative. So let's talk about the coding part, how we can implement this O of n plus m time short code. Okay, you can see the time complexity is O of n plus m and space complexity is O of n plus m. If we neglect the, you can see the recursion stack space. Okay, because I'm going to use a recursive function to get the elements using in-order traversal. Okay, so you can see I have a get elements function that uses in-order traversal, that stores all the elements in ascending order. So if this is the standard template, you can also say, for in-order traversal. So first we will visit the leftmost node, then root node, then the right node. So you can also understand the standard way of in-order traversal is like this one: root, then sorry, it is not actually the root. So it is like left node, then visit the root node, and then visit the right node. Okay, always follow this policy. Suppose you have a binary search tree or a binary tree, it doesn't matter because we are talking about the traversals. Okay, so let me number this node 1, 2, 3, 4, 5, 6, 7. So if you follow this policy, it says you are always going to move to the left node first. So if you are at 1, go to the left node. Still it has some left node, go to the left node again. So you are going to visit 4. Now 4 doesn't have any left node, so you are done. So you will check out for the root node of the current node, which is you can see yeah. So you have already visited 4, so you will come back to this node 2. Okay, now node 2 has left child, but it is already visited. So now the policy begins for the right node. So you will go to the 5. Now it is done. So you will come back again. You can see this entire subtree has been done for this node. So you will again go to the root node of this one. So it will be 1. Then if you follow the same pattern, you will get yeah. So you will get 4. Let me write down the nodes 1. Yeah, 4, 2, 5, 1. Then again 6, 3, 7. I think this is the actual traversal. Yeah. So might be I will be doing something wrong. Yeah. No, I think I'm correct. Yeah. So you can see. Let me just correct it up if I am doing something wrong, because that makes you quite worried. So this is 1. First I will visit this 4. Yeah. Then left node, and then again 2, 5. Then again 1, 6, 3, 7. Yes, I am correct. Okay, so you are going to use the in-order traversal, left node, root node, and right node. Okay, so it will give you the elements in the sorted form. So what I am going to do is, like, I will get all the elements in these two vectors, element 1 and element 2. So it will be like passing the parameters as root and its vector corresponding to that. This will fill all the elements in the in order fashion, you can see. And finally we need to merge these two arrays in O of n plus m time. That is a linear time. So we'll take two pointers L0 and R0 corresponding to each of the vectors, and n and m is going to denote the vector size respectively. So we will iterate for the first, like L is also less than n and R is also less than m. Then we will compare the elements, then we will push back them and increment their pointer respectively. Now it might be possible that after the operations has been done, some vector, like exactly one vector, at not saying it at exactly, at the most one vector might remain empty. So you will push back all the elements from that only vector. Okay, so you can see these two functions are doing the same. So and finally return the answer. This will give you all test cases passed. Okay, now there is another approach that is going to follow iterative fashion. So this is totally based on in-order traversal. If you know the concepts very much well, using the stack. That is, stack is used to find out the in-order traversal of a binary search tree. While you are using the stack, you can also find out, like, compare the elements respectively using the same operations of finding the in-order traversal. Okay, so let me just explain you in the simpler words. Suppose I have two binary search trees. Okay, so let me say I have this binary search tree. So what we are going to do is, if you know the iterative version of the in-order traversal, first it will visit the leftmost node. So this is the very first node, you can see. Yeah, this will be the very first node. Let me circle it. So this is the very first node, and let me circle another node for this binary search. So this is the very first node. So our first criteria is visit the first node using the iterative way of the in-order traversal and compare these two nodes values. Okay, so you can see these two are the minimum values among the respective binary search trees. Let's call this as A and let's call this as B. Okay, now what happen if A is going to be like less than or equal to B? So if A is going to be like less than or equal to B, it completely says that we need to first push back the element A, the value A, into our answer. So if you will push back the value A into your answer, you need to move to the next node of this binary search tree to compare with the value of B, right? Because you need to push back the elements in the sorted way. So if you are done with this A, that is this value A is taken, the next node, so that should be taken from this binary search tree 1, let me call this as 2, is going to be like this node, and let's call this as value C, because this A is taken. Now since we need to fill the elements in the sorted form containing both the elements from both the trees, you need to compare C and B. So you will compare C less than or equal to B, it might be possible, and C greater than B, it might be possible. So suppose C is going to be like greater than B, so in that case this element is going to be used. So you are going to move to the next element of this binary search tree 2, that is going to be, let me encircle this one. Okay, so again you need to compare value C with the value D, let's call it as. Okay, so in that way you're going to use to move to the next node. If this element is going to be done, exhausted, that is used, that is pushed back into our answer, that is going to be returned, then you are going to move to the next node of the corresponding binary search trees. Okay, so this is going to be the entire concept. The only difference that makes it different from the recursive way and iterative way is the concept of iterating and finding out the in-order traversal of the binary search tree. Okay, so you need to learn, or recursive way, let me say, you need to learn the recursive way of finding the in-order traversal of the binary search tree, and iterative way. Just understand the procedure to do that, then you can solve this problem at your own risk. Okay, so let me just explain my code. So this push next is a method that is going to push up the next node of the current node if you look out for the in-order traversal of the current tree. Okay, so suppose you are at this root 1 and root 2, the respective nodes of the binary search tree, and there is a stack that is going to perform the iterative version of the in-order traversal of the binary search trees. Okay, so you are at this root 1, you need to push up the next node of this root 1, that is the very first node of the in-order traversal of the tree 1. So you will use the push next method. You can see it will go to the node's left, extreme left node, that will be the very starting node of the binary search tree, which will be the first node if you consider the traversal in the in-order fashion. Okay, so you need to compare the methods right now. So we will do until either of the stacks, like both the stacks are not empty. So if first stack is empty, you will work on the only second stack, that is the second binary search tree. Okay, so you will push back, like, the every time you are going to have the stack top having the next node of the in-order traversal of the binary tree corresponding to the next node. Okay, so you will push back the node's value, and if this value has been exhausted, you will go to the next node considering the in-order fashion of the second binary search tree. You can see we are working on the S2. because S1 is empty. So you can see I have taken this node value and I am going to go for the next value, next node corresponding to the in-order traversal of the binary search tree 2. Now what will happen if S2 remains empty? So if S2 is empty, it means that all the elements of this binary search tree 2 has been exhausted. So we need to work upon the first binary search tree. That's why we are working upon the stack S1. So pick out the very first node, which is the corresponding, like the very current node of the in-order traversal of this binary search tree 1. So we will push back the nodes value and we will store the next node in the in-order fashion of this binary search tree 1. You can see push next S1 comma nodes right. So this is totally based on the iterative version. Now what will happen if S1 is non-empty and S2 is non-empty? So you need to check it out which node you are going to work upon. So if S1 tops val, that is the corresponding candidate of the very topmost node or in the in-order traversal of the corresponding binary search trees, you are going to compare the nodes values. If S1 tops val is going to be less than or equal to S2 tops val, then you need to pick out the node as node of this binary search tree 1 and you will work upon that and storing the next node. Otherwise you are going to work upon the binary search tree 2, the candidate node, like the topmost node present in the stack S2. And if all goes well, you can see you are going to have the sorted form, because in-order traversal always works in the sorted way of the array elements if you consider the tree as a binary search tree, and finally return the answer. This will have this will get you all test cases passed. You can see the difference in runtime because of the maybe the recursive stack and also the memory, because the iterative version is quite faster. So if you guys have still any doubts, do let me know in the comment section of the video, and thank you for watching this video.